Okay, sir. Wait for 1 minute, sir. Maria, are you ready?
Yes, sir. Yes, sir.
Okay, right. Okay, good evening to all. This is Adar Lanjaya, working as assistant professor in Triple Department and IEEE TLS chapter advisor at TCARSET. Right now, one event is going on, that is online webinar is going on multi-level inverters for renewable energy systems. So, our IEEE PLS chapter student branch chapter counselor Maria Maha will introduce the about event and resource person. Maria can carry
Yes,
on
sir.
right now.
Good afternoon to one and all. I warmly welcome all the respected dignitaries, faculty members, and dear students who have joined us today. I hope everyone is doing well. On behalf of TKR College of Engineering and Technology, the Department of Electrical and Electronics Engineering, and the IEEE Student Branch TKR SET, it gives me immense pleasure to welcome you all to this IEEE online webinar. Myself, Sayed Maria, Student Chair of IEEE Power Electronics Society, Chapter IEEE Student Branch TKR Set, and it is my honor to anchor today's technical session. This webinar is organized by TKR College of Engineering and Technology, Department of Electrical and Electronics Engineering in association with the IEEE Universal Studies Bureau, Los Angeles Section, IEEE Electronics Society, and IEEE Student Branch TKR Set. The objective of today's webinar is to provide participants with both conceptual and practical insights into multi-level inverter technologies and to understand their crucial role in modern power electronics and renewable energy systems. This topic for today's session is multi-level inverters for renewable energy systems. It is my great pleasure to introduce our distinguished speaker for today's webinar. We are privileged to have with us Professor Dr. Sanjiv Kumar Sir, Dean of International Student Affairs and Professor in Department of Electrical Engineering. Dr. Sanjiv Kumar Sir earned his PhD from Indian Institute of Technology, Roorkee, where his research focused on performance enhancement of multi-level inverters for induction motor drives. His core areas of research include multi-level inverters, high power converters, industrial electric drives, and power electronics. With distinguished academic careers spanning from assistant professor to a professor of Harcourt Butler Technical University, he has made remarkable contributions to teaching research and institutional development. He is a senior member of IEEE and a fellow of the Institution of Electronics and Telecommunication Engineering, IETE, reflecting his professional excellence and recognition in the electric engineering community. Dr. Kumar has authored books, published numerous research papers in the reputed journals, including IEEE Transactions, and has successfully guided several PhD scholars in the domain of power electronics and electric drives. His dedication to research and academics continues to inspire students, researchers, and professionals alike. We are truly honored to have such an eminent academician and researcher with us today. I am confident that his vast knowledge and experience will provide valuable insights into multi-level inverter technology and its real-time applications in renewable energy systems. Now, without further delay, it is my proud privilege to invite Professor Dr. Sanjeev Kumar Sir to deliver his keynote talk on multi-level inverter for renewable energy systems.
Thank you, Maria, for such a wonderful introduction. As the topic of today's talk is multi-level inverter for renewable energy system. See, nowadays everyone is talking about renewable energy, right? So, multi-level inverters plays a vital role whenever we want to convert any DC voltage into AC. Because see, when we have two level inverters, then there are several problems. To overcome those problems, we go for multi-level inversion. We will see in today's talk, and the time allotted to me is only 1 hour, so it was really challenge for me to cover this wonderful topic within 1 hour, but I might try level best, right? So let us start with two-level inversion operation. These two-level inverters are used in ASD, adjustable speed drive, UPS, uninterrupted power supply, high voltage DC transmission, active power filter, photovoltaic system, etc. The problem associated with these inverters is like they suffer problem of harmonics, right? They suffer the problem of harmonics. Not only this, there is a problem of high dvy dt. See, whenever we apply voltage on the device and the switching frequency is high, then problem associated with the high dvy dt also come in the picture. Not only that, if the switching frequency is high, then this switching losses are there. Moreover, why we make this switching frequency high? Because we want to have sinusoidal voltage at the output side. That is why by applying the PWM technique, we try to get sinusoidal voltage, and for that we have to make the switching frequency high. And this high switching frequency pertain to switching losses. Consequently, your inverter efficiency goes down, right? And another problem, we have to connect several devices either in series or in parallel to have the I mean to meet out the voltage and current rating, right? That we have to take care of those things, right? Now I'll make a simple slide where you can see how this multi-level inverters are applied everywhere. How these multi-level inverters are applied everywhere. Here you can see we have variable speed drive, where first you have to convert this AC into DC, then after DC you have to convert this DC into again AC, right? Then we have this traction application is there. Then if we talk about the utility interfacing, we can use these as a active filters and devices. We are using multi-level inverter. HVDC we are using multi-level inverter. StatCom we are using multi-level inverter, right? Now in today's world, everyone is talking about the multi-level, this electric vehicle, hybrid electric vehicle and electric vehicle. There also we can use these multi-level inversion operation, right? We use these in DTC, that is direct power control, as well as field oriented control. There we can apply this multi-level inverter, right? Then come to the renewable energy system. As the topic is that for PV cell application, we apply this photovoltaic system. For photovoltaic system, we use this, right? Now, if we talk about wind energy application, then again we use this multi-level inverter. How we use this multi-level inverter? See, wind velocity, wind speed is not in our control. So what we do, we have induction generator, and the frequency of that induction generator is not meet out the grid frequency. So what we do, we first convert this AC into DC, then again we convert this DC into AC by using the inverter, right? So there we use this multi-level inverters. Right? Now come to the type of multi-level inverter. Before telling the type of multi-level inverter, I would like to uh, discuss what exactly multi-level inverter is. See, you can see the figure that here is one voltage source and one switch. The first one, figure A, you can have two voltage. Its pole is having two voltage, one is 0, other one is VC. This is simple two level inverter. Now if we talk about the three level inverter, then here you can see this voltage could be minus VC, this voltage could be this voltage could be 0. When the switch is connected here, it would be 0, and when this switch is connected mid of this, then this would become the plus VC, and when we connect this at the top, then it would become the 2VC. So this figure B can have three values, 0, VC and 2VC, right? Similarly, this is n level inversion operation, 0, VC, 2VC, so on and so forth, right? Now, if we talk about the multi-level inverter, the advantage of these multi-level inverters are numerous, like very low dV by dt distortion, very low dV by dt distortion, very low dV by dt, as well as see the number of steps are increased. Now, when number of steps are increased, the output voltage is less distorted, means that is nearer to sinusoidal. For having sinusoidal voltage, you have to have the number of levels should be infinite. Ideally speaking, it should be infinite. But as the number of level increases, the number of switches also increases, and it would become very difficult to manage all these switches and all, right? So that is the problem. Now this they draw input current with very low distortion. Reason is, as the voltage becomes the sinusoidal, approaches towards the sinusoidal, so the input current has to be improved, right? Not only this, they generate very small common mode voltage, right? That ultimately reduce the stress on the bearing, right? And see, if we properly select and apply the sophisticated modulation method, then we can even eliminate the common mode voltage. Another advantage of this is they operate at very low switching frequency. They operate at very low switching frequency. That is the another advantage of this type of inverters. Now in the market, these three, see, there are another researchers keep on doing the work on this, and these three, what exactly I am discussing in this particular talk is very simple. I just thrown some areas where researcher can do something good, right? That is the motto of delivering this talk. So here you can see we have three type of uh, let me take the highlighter. We have three type of inverter. One is diode clamp multi-level inverter, another one is flying capacitor multi-level inverter, and next is the series cascade H-bridge inverter, right? Series cascade H-bridge inverter. Just Okay. Now, then I should take pen rather than taking the highlighter. Now it is fine. Now, see, this is 3-level diode clamp inverter. Let me also change the color of this. See, it would be very good if you uh, ask question in between. That will make your doubt more clear, right? So that would be the good thing. Here you can see, and most of the participants are PhD, as organizer has told me. So I believe they will get something good from this talk related to their research, right? So this is this is 3-level inversion operation. We are measuring the pole voltage with respect to this neutral. So when these two devices are on, then this voltage is minus VDC by 2, and when upper two devices are on, then we would have plus VDC by 2, and midway it is 0. Similarly, we have 5-level inversion operation. There you can have this. There you can have, when all these switches are on, you would have VDC by 2. When these three on, you would have this VDC by 4. Then you have 0. Then you have minus VDC by 4. And the last is minus VDC by 2. So you can say it is 2 VDC by 4, VDC by 4, 0, minus VDC by 4, and minus 2 VDC by 4. This is the same circuit. I have redrawn this. This is the operation for diode clamp inverter, right? For voltage level VAN is equal to VDC by 2. What we have to do, all upper devices must be on, as I have already told you. And for voltage level VDC by 4, what you have to do, you have to turn on all three upper devices and one from lower devices. So that switching pattern is very simple, and most of the students and participants already know this. Likewise, we can have 5-level inversion operation. And if we talk about the flying capacitor multi-level inverter, we can notice that when you see the flying capacitor multi-level inverter, here what we do, we connect several flying capacitor such that we could obtain the desired voltage level. See here, each capacitor, you can see this DC link is divided, into two part. One is this VDC by 2, other one is minus VDC by 2, and each capacitor is maintained at VDC by 4. So C1 to C, all C1 means, all C1 means this, these two C2, and all this C3, all are having voltage VDC by 4, right? So if you see, I'll explain this. For example, if you wish to have voltage level VDC by 2, what you have to do, you just turn it on. So all switches on, and this point is connected here. So this voltage VAN is equal to VDC by 2. Now for voltage level VAN, is equal to VDC by 4, you are having three combinations. You can have this using any of the three combinations. The key features of this flying capacitor multi-level inverter is this: you have to maintain the capacitor voltage balance. Otherwise, your multi-level inverter will not give you the desired output once the capacitor voltage become unbalanced. So what you have to do, you have to make it balanced. So for that, what we do, we sample each and every data, the voltage of the capacitor on each sample time, and do corrective action. See, when the current is flowing from in one direction, let us say it is the current is flowing like this, the current is flowing like this in this capacitor, it is getting charged. And when the current is flowing in this direction, it is discharging itself, right? So by changing the direction of current, we can charge the capacitor or discharge the capacitor. So what we do when we operate on this multi-level inverter, flying capacitor based multi-level inverter, we keep on checking the voltage level of the capacitor. When the capacitor is overcharged, we operate it in such a way that the direction of current is changed, but the voltage level remain the same. So that way we will do. Those who are working in the field of like this multi-level inverter, they know these are the very simple thing which I am explaining. Similarly, for having the voltage level 0, we have six redundant switching. By using any of the switching, we can get the 0 level, means VAN would be 0. But we should remember that we sample the capacitor voltage in every sample time or in two sample time, depending upon the logic, depending upon the philosophy which you have used. And once you measure the capacitor voltage, what you have to do, you have to take the corrective action. You have to take the corrective action so that capacitor charge must be maintained, capacitor voltage must be maintained at constant level, VDC by 4. That we have to do. That we have to do. Right? Now after that, next is series, or we also call it cascade edge bridge multi-level inverter. This capacitor multi-level inverter, edge bridge based multi-level inverter, this is very simple in construction and having the modular approach. This is one module, right? So we have connect several modules in series and get the, look at this, sorry, you will get the voltage. See, each module can have 3 level of voltage. It can have 3 level. This is VDC by, let us say this is VDC. So it could be VDC, it could be minus VDC, and it could be 0. Likewise, all 4 modules are having this much voltage. Here you can see the fourth one is giving this much voltage. The V3 is triggered such that it will start giving voltage like this, and so on and so forth. So the final voltage waveform which you get, that would be like this. That would be like this. Right? It would be like this. Right? So on and so forth. So this is how we do. This is how we do. Now, this is 9-level inverter, 3-phase 9-level inverter, cascade edge bridge type. So now the features of various topology is also being compared, that diode clamp multi-level inverter that required the very high voltage rating required for blocking diode. Not only this, unequal voltage rating, device rating is unequal. If you remember that the diode which was I have redrawn the circuit here, you can see that this diode is blocking, let us say, X voltage. So this would block 3 times of this voltage. So what we do, we have connected 3 diode in series. See, ultimately we have to sell this sell this inverter to the outer world, and it would become very difficult for spare management point of view if we use different rating of device. So what we do, we simply use the same rating device and we connect number of devices in series or parallel. So that is what we are doing. We are connected these three devices. Here this is the higher voltage, so we have connected these three devices. Likewise we do in all the phases. Right? Another thing that, see, these switches conduction is different. You just see SA1 is required to be operate only when V5 is equal to VDC, and most of the time it is not operated. Whereas SA2 is required to be operated to have voltage. Yes, if you wish to ask anything, somebody has opened the mic. If you have any doubt, please ask, otherwise just shut down your mic. That would be great. Right? Now you can see here the this device is on for this much duration, means for having VDC V5 is equal to VDC or V4 3 VDC by 4 or V3 VDC by 2 or V2 VDC by 4. To having all these four levels, this SA4 has to be operated, needs to be operated, means turn it on. Right, whereas SA1 is only for a small duration, that is only for the duration of when V5 is equal to VDC. So this type of unequal device rating create problem. Yes, if anyone is having any question, please ask. Likewise, the capacitor which we have connected to say bifurcate the DC link, that capacitor is also having the unbalancing and balancing. They are having the unbalancing. These are shown in this figure, right? So this advantage and disadvantage I have already covered. Now I would show you the main comparison of these topology. You can see for M level inverter, we have require main switch same for diode clamp, line cutoff, and this is cascade edge bridge multi-level inverter. Right? Main diode is also same. But if you talk about the clamping diode, it is required only in the case of diode clamp, whereas flying capacitor both are not required anything. Now if we talk about the DC bus capacitor, both flying and this diode clamp required M-1 for M level inversion operation, whereas CHB required only M-1 by 2. That means DC bus capacitor rating goes to 50%. Now if we talk about the balancing capacitor, it is only required in case of this flying capacitor multi-level inverter. Here, flying capacitor multi-level inverter. Clear? Now you see, let us say if it is 10 level, 9 level or 13 level inversion operation, huge amount of switches are required. So researchers try to find, this is the area of research, that we should get some topology in which less components are being used and they give the maximum number of level. So that is the area of research. Keeping this thing in mind, researchers have developed one topology that is based on the open and winding induction motor. Right? And see, in case of renewable energy, it could be open end transformer. Rather than putting it in the star or delta, you can open the transformer both ended. I mean, the neutral has to be open, and the inverter can be fed to the this open and winding transformer. One of my research scholars is working on this. he is about to submit his thesis, and there we have used this type of concept which we have earlier applied on the open and winding induction motor. Right? Here what we do, we just open the neutral. We just open the neutral. We just open the neutral. Let me take some this. I can hear some mic is open. So this lecture is live, and if you have any doubt, please ask. Otherwise, just shut down your mic. I request to coordinator, please check if someone mic is open, either remove him or her, or just asks to turn off his or her mic. Otherwise, it is very difficult for me to move forward. Let me also check. Just give me a second. Just give me a second. Just as the number of participants is quite high, so let me allow to take the screenshot. Just give me a second. Whose mic is on? Maria,
Yes, sir.
please check whose mic is on.
Yeah, okay, sir.
Just check. And I'll also check. Yes, Anji, your coordinator Saab mic is on. Meeting host mic is on. Please ask him to mute himself.
Okay, sir.
Huh? Because it distracts my thought process. So it would be great if you turn off the mic. Just give me a second. Let me just give me a second. See, I am just sharing the my screen. Just give me a second. My screen is visible. My screen is visible to all of you.
Yes, sir, your voice is coming.
My voice is coming whether my screen is visible to you or not.
Not, sir. Not. It's not coming, sir.
I think
Share it once. Okay.
the screen is coming or not.
So it is visible, sir.
Yes, sir. Yes, sir. Coming, sir.
Now it is coming, na? Oh, good.
Yes, sir.
Good.
Okay, sir. Carry on, sir.
Just a minute. Now fine, it is coming.
Yes, sir.
Good, great. Just a second. So this what researcher did, we have opened the neutral of our induction motor. We have opened the neutral of our induction motor. Now we have three just take the this. We have three terminal this side and we have three terminal this side. Now what we did, we have connected, this is my research work that I am going to show you, that this here we have connected one two-level inverter and here we have connected another two-level inverter. So from both side of the induction motor stator winding we are feeding this, right? The same thing we can do for feeding this grid side to connect the PV cell and all, right? We will use the transformer with open end winding. Please don't make your mic on. If you have any doubt, please ask. I am
హైదరాబాద్ అండి.
repeating. Yes, I think Maria is.
హైదరాబాద్ అండి మీరు?
Please turn off your mic. Now, this is our structure of two-level inverter. 6 devices: S11, S13, S15, S14, S16, and S12. Right? Whenever if we talk about the pole voltage, whenever this switch is on, we get the VDC by 2, and whenever this switch is on, we get voltage 0. So inverter 1 can have 3 pole voltage 0 0 and VDC by 2, whereas inverter 2 can have pole voltage VDC by 2 and 0. So inverter 1 pole voltage either it could be 0 or VDC by 2, whereas similar type of inverter is used at the right hand side, so that can also have the value 0 and VDC by 2. Now we can operate in such a way that one inverter is having 0 voltage, another one is having VDC by 2. So overall we can have minus VDC by 2, 0 and plus VDC by 2. Overall we can have minus VDC by 2, 0 and VDC by 2. We have used two-level inversion. We are using two-level inverter and we are getting three-level inversion operation. This is the switching state for this, and this is how we have derived the mathematical modeling of dual two-level inverter. Very simple concept is being used and we get this, right? And this is the MATLAB simulation model. If you wish to go in detail, I will share in the last my YouTube channel link. There the detailed simulation of open and winding the induction motor is given. I have taken lecture at SVNIT Surat, I think. So that type of lecture you can find there, and you can have this simulation and modeling everything. Right? Now we have investigated the performance of this by doing the simulation, and V by EF control is used for this, and switching frequency is kept 1 kilohertz, and the DC link voltage is selected as 600 volt, and we operated the motor at no load and at the modulation index 0.2, 0.8 and 1, right? So corresponding frequency would be 10, 40 and 50 hertz, and these are the phase voltage waveform. You can see the phase voltage waveform is having this two-level inversion operation at lower modulation index of 0.2, which at which the frequency is 10 hertz, and if you see the TSD, the biggest problem of two-level inverter, TSD is 132.53% in the voltage. Output voltage TSD is quite high, so it is not good. It is not good, right? So to overcome this, what we did at the in fact at the 40 hertz, that means modulation index 0.8, still the TSD is quite high, 32.18%, 32.18%. So this is not so good. So this I am skipping, and the motor is of course tested for the steady state and transient state performance. We have changed the modulation index from 0.2 to 0.8. So voltage, output voltage waveform change instantly, but the current, it takes some time to get again stabilized. Whether it is a means low to high change or high to low, means the modulation index is 0.8 and we have changed from 0.8 to 0.2. There is that one typographical error, so kindly pardon for this. In the both figure it is mentioned 0.2 to 0.8, right? Now we have extended our topology and made the 5-level inverters for induction motor drive. In that, what we did, we have one 3-level inverter at the left hand side by cascading simple 2-level inverter, and at right hand side we simple 2-level inverter, right? So when we do this, what we get? We get 5 level, minus VDC by 4, 0, VDC by 4, 2 VDC by 4 and 3 VDC by 4. Basically VDC by 2 is 2 VDC by 4, isn't it? Now this is the space vector distribution of 5-level inverters. Now if we properly select the DC link voltage, and to select this DC link voltage, the formula is like this: VDC by 2 VDC by N is equal to N2 minus N1 divided by N2 times N1 minus 1. The same structure, the same circuit which we have used earlier, the same circuit is being used, and we get the 6-level inverter. See, as the number of level increases, we increase the this TSD, total harmonic distortion, is also reduced. So it is always good to have higher number of level at the output side, but to have it, the switch number of component requirement is high. So that is the thing which we should keep in mind, and this is the how we have developed the hardware model for this, that is inverter A and inverter B, and we have developed the controller on the Opel RT system. We have taken the analog input for voltage and current measurement if it is required, and then we generate the gate pulses for the both inverter, and these gate pulses are fed to the isolation circuit, and this isolation circuit generate the pulses for the deadband circuit. See, deadband circuit is required. Why it is required? It is required that there should not be any dead short circuit. If the device of same leg get on at the same time, then there is a dead short circuit. To overcome this, we use this uh, dead band circuit, right? So that is the principle for funda behind this. Now it is fed to the IGBT driver circuit, and this driver circuit feeding the gate pulses to the various inverter. And this is the hardware which we have developed. This is our 3-phase open and winding based motor, and these are the voltage and current sensor. This is the host PC of that Opel RT system, and this is our DSO. This is isolation and deadband circuit, and this is the our inverter A and inverter B. Upper is the inverter A, lower one is the inverter B. This is current sensing circuit, voltage sensing circuit. This is simply the pictorial view. You are not able to getting anything from this. No problem. In case if you require anything, or if you wish to do work in the field of power electronics, you can contact me. I will share in the last slide that my contact number and everything to all of you. And this is the complete hardware setup of this. And these are the experimental results. This is for modulation index 0.2, and you can see the same result earlier we have got that in simulation. The same type of result we are getting in the hardware, 1-to-1 correspondence. This is the at modulation index 0.6, and the frequency is 30 Hz. You can see the output voltage, how it is going close to sinusoidal, so TSD automatically get reduced. right? And this is at modulation index 0.8. You just see the waveform. You just see the waveform. It is going near to near sinusoidal. Going near to near sinusoidal. Right? And the TLD is reduced and reach up to 7.11%. Still it is quite high. We have to reduce it further. So for that, what we did, we use this 9-level inversion operation. We use this 9-level inversion operation. Here what we did, we connect 4 2-level inverters in cascade way, 2 at left side, 2 at right side. So both side is feeding the voltage level. That means three level inverter is achieved using the 2-level inverter. Left hand side inverter can give you 0. It can give you 0, 3 VDC by 8 and 6 VDC by 8, whereas right hand side inverter can give you 0 VDC by 8 and 2 VDC by 8. So overall this combination give you 9 level of inversion operation. Here you can see it is giving 0, 3 VDC by 8 and 6 VDC by 8, whereas right hand side inverter can have 2 VDC by 8, 1 VDC by 8 and 0, and similarly this pattern is going on. So you can notice one thing, the inverter which is having higher DC link voltage operate or switch less. What is the advantage of this? The advantage of this is the switching losses reduce. The inverter which is having less DC link voltage, that is switch fast, that is switch in high, switching frequency is high of that inverter which is having less voltage level. So that the losses are reduced and the efficiency is also improved. And if you look at the phase voltage, what we get, minus 2 VDC by 8, minus VDC by 8, 0 VDC by 8, 2 VDC by 8, 3 VDC by 8, 4 VDC by 8, 5 VDC by 8 and 6 VDC by 8. These are the 6 level which we can have. To achieve this level, the switching combination is shown here. I am not going to detail of this. Now just have a comparison on this. The proposed means the topology which we have discussed. Just see how we have successfully reduced the various components. See, the DC link of this VDC is required in neutral point clamp and flying capacitor, whereas it is not required neither in CHB, ACHB or in the proposed topology. Fine. DC link of VDC by 4 is required by asymmetrical edge bridges 3, whereas it is required only 2. Now DC source of VDC by 8 are required in CHB is 12, ACHB is 3, whereas in R it is only 2. If we talk about the VDC by 8 rating IGBT, all conventional inverters required 48, whereas ACHB required 12 and ours required 6. So in the same way we can see our inverters required less number of components as in comparison to the various topology available in the market, right? And this is the space vector diagram of this, and this is the modulation scheme which we have used, that is the space vector PWM. I have referred the Professor K. Kumar sir paper for this, and this is very very interesting that we can have the equivalent performance as we can have in the space vector modulation. Same type of performance we can have here by simply using the sine wave, right? So there is one paper, if you wish you can refer that, and these are the hardware results, and it shows that the TSD at modulation index 0.42, the TSD is 0.3, 3.20, whereas when modulation index is zero point 0.8, the output voltage TSDs come out to be 2.27 and the current TSDs come out to be 1.03. So in that way it is good. Now this motor is also evaluated for transient state performance. Here you can see the modulation index is increased from 0.2 to 0.8. The voltage instantly it will be changed from 2 level to 9 level. But if you talk about the current, it takes some time. And after 5 to 10 oscillation, it is attending its steady state. So not very bad. It's fine. Similarly, we did the experimentation from zero point 0.8 to zero point 0.2. We changed the modulation index from 0.8 to 0.2 and it is found that voltage is changed instantly, whereas this current take few cycle to get settled, right? So the summary of this is the motor phase voltage waveform becomes more and more smoother as the modulation index increases and approaches towards sinusoidal. Higher DC link voltage is switch less, whereas lower DC link voltage is quite high. High means done and we have already taken the switching frequency only 1 kilohertz, so it is not that much high. And moreover, this is very less that DC link voltage is the switch which is puzzle the high DC link voltage, that switch quite less. So that is the best thing of this inverter, right? So this is the next topology, that is hybrid 9-level inverter for induction motor drive. Here what we did, we have used one cascade edge bridge, flying capacitor base, and this. By this we, and right hand side is having simple 2-level inverter. Here the key feature is again the voltage of these two capacitors VCC1 and VCC2 for phase C, and similarly for phase B and phase A. There are total six capacitors. The voltage of these capacitors has to be maintained constant for successfully operate this topology. Right? That has to be proper. Right? And here you can see, for let us consider, see, although this can generate this level, but because there is no redundancy, so we have not used these switches. Clear? And for others, there are redundancy, so we are operating like this. You can see for this level there is no effect, and for level B minus 3 VDC by 8, this there is changing discharge, charge. There are several states. Means whenever we have to keep the measurement of direction of current as well as the capacitor voltage. We check if the current is flowing in particular direction and the capacitor voltage is overcharged. We take that switching combination which produce the discharge. Here you can notice here this for the same motor phase voltage minus VDC by charge, this switching is charging capacitor CA1, whereas it is not doing anything with capacitor CA2, whereas for the same voltage this switching is discharging this capacitor. So you can see notice the voltage level. If it is overcharged, you use the operation which discharges, and if it is voltage goes down, you can choose the operation which get charges. So this is the all switching frequency. One of my paper in, I think, Taylor and Francis is available on this particular inverter, so you can refer that one, right? And this is the generation of different voltage level. So you can see by this type of switching we can have the voltage level minus VDC by 2, because this is at VDC by 2 and this is at 0 level. This is at 0 level. So 0 minus VDC by 2 is minus VDC by 2. Clear? Similarly, here you can see another redundant switching is this, like this. Clear? So this type of thing we can achieve. Now if we compare the component, I know that the time is going very fast. I have only 2-3 minutes. I'll try my level best to finish within an hour. So this DC sources, if you compare this, our topology doesn't require any voltage source of DC link VDC. If we talk about 3 VDC by 8, your ACHB required 3, whereas our topology doesn't require anything. If we talk about VDC by 2, cascade edge bridge required this hybrid multi-level inverter, whereas R required also 2. So both are same. Now if we see number of IGBT of VDC by 8 rating, our required 12, whereas these three conventional required 48. And add all three topology here required, all these three topology required same, but gradually we succeed here. We required only 6, and we 6 IGBT of rating VDC by 2. We required capacitor of VDC by 8 is 9, whereas if you compare this flying capacitor, it required 84. So moreover, more or less, these our topology uses less number of component as compared to the others topology, and this is the control strategy for the capacitor design, right? We have used that the capacitor ripple in capacitor current, and we measure the voltage in every sample time. So in every sample time it is get corrected. Here you can see this voltage is almost constant. This voltage is almost constant. These are the capacitor voltage, and the TSD is for modulation index 0.16, it is 42. And if you see in the last, I am just skipping this. Let me show you this. The voltage rating, which is here 0.8, it is 0.8. You can see this modulation index is 0.8, and just see the voltage profile. Just see the voltage profile. It is almost sinusoidal, right? And this is the capacitor voltage, which is maintained at 48 volt VCA1, and this is the VCA2, which is maintained at the 25 volt. Of course, there is a variation of plus minus 2 volts. So within 50 as compared to 50, it is less than 2 volt by 2 volt, and settle at 48. And if we talk about the VCA2, it has to be at 25 volt, but it is maintained at 23 volt. And I'll show you the transient state behavior of these capacitors. Here you can see we have intentionally disabled the capacitor voltage balancing logic at this point. So you can notice that we see where A1 is keep on increasing and reach somewhere around 80 volt. Consequently, the current and this output voltage waveforms are also getting distorted. And again at this point we enable the capacitor voltage balancing logic, and it comes down very quickly. Very quickly it's come down. Similarly, the same type of thing we have applied for here, means intensely we disable the capacitor voltage logic at this point, so this voltage is increasing, and when we enable it, it comes down to its original position, right? So these two things you can notice that in this only two DC sources are required, right? And the effectiveness of the capacitor voltage balancing is carried out as we keep on the balance in the every this sample time. So this is all from my side, and these multi-level inverter could be widely used, and there is a tremendous amount of research in this particular field. I have shared the this my WhatsApp number and my link of my power electronics channel. If you wish, you can visit this. I am going to show you. Let me check if it comes. Just give me a second. Just give me a second. Just give me a second.
Okay, Maria.
Just give me a second. I am going to show you. This is my channel, and your lecture is also live here. Here you can see this, right? So if you wish, you can go through your lecture as well, and I suggest that if you like, you can subscribe my channel and go through all these lectures. I have shared in the chat box. Participant can go through the link. I hope everyone got this. So this is all from my side. Now over to you.
Thank you very much, sir, for such wonderful and insightful session.
Maria, just turn on your camera. At least participant can see the organizer. That is my suggestion. Whenever you conduct any online webinar, it is always supposed to be that organizer must turn on his or her camera, so that at least participant can see who is going to organize. That is only the suggestion. Over to you.
Okay, sir. Thank you very much, sir, for your wonderful and insightful session. Your clarity of thought and ability to connect theory with real-world applications made this session truly engaging and meaningful. We feel privileged to learn from your vast experience, and we sincerely appreciate your efforts in guiding and motivating us today. Through this session, we have gained valuable and in-depth knowledge about multi-level inverters technologies and their practical applications. Concluding the session, I would like to invite Sai Rudramesh, Vice Chair of IEEE Power Electronics Society, to deliver the vote of thanks.
Good evening, everyone. As we come to the end of this highly informative webinar on multi-investors, it's my privilege to propose the vote of thanks. First and foremost, I would like to express my heartfelt gratitude to our esteemed speaker, Professor Dr. Sanjiv Kumar Garu. the senior member IEEE, and the Dean of the International Student Affairs and Professor in the Electrical Engineering Department at Harcourt Butler Technical University, Kanpur, for delivering such an insightful and enriching session. Your expertise, depth of knowledge, and ability to explain the complex concepts with clarity have truly inspired all of us. We sincerely thank the IEEE PLS Society TKRSET and the IEEE Student Branch TKRSET for successfully organizing this webinar and creating a platform for learning and innovation. I would also like to extend my appreciation to the faculty coordinators and the student volunteers whose dedication and teamwork made this event possible. A special thanks to all the participants for your energetic presence and active engagement. Your involvement made the session interactive and meaningful. Finally, we are grateful to everyone who worked behind the scenes to ensure the smooth execution of this webinar. With this, we conclude today's session. We hope this webinar has enhanced your knowledge and sparked greatest interest in the field of power electronics. Thank you, thank you once again. Have a great day.
And see, this lecture is live